Okay, so if you did not, if you weren't able to watch my previous lecture from the other day, it's okay, just watch it after class, it's on Blackboard. I'm going to be covering topics from that lecture though. I'll try to remind everyone, if you haven't watched the video, I'll show you the definitions that you need. But this is the lecture 2. And we'll be looking at propositional equivalences. So in the previous lecture, we introduced this definition of a proposition. So a proposition is a declarative statement that is either true or false. So for example, in the previous lecture, I used UHD is a public university. Declares a statement and it's either true or false. It happens to be true. And so you would say the truth value is true, capital T, true. And another proposition would be 2 + 1 is equal to 5. It declares a statement and it happens to be false. So its truth value is false. Okay, so maybe I'll write down the definition just so you remember that the proposition is just a declarative statement. Is either true or false. And for notation, I use capital T for true. And capital F for false. Okay, so and for notation, we'll typically use lowercase letters to denote propositions. So then we can act on them using operators that I introduced last time. And these operators are the negation operator, which takes the opposite truth value. So like if P was the statement UHD is a public university, not P would be that UHD is not a public university. So they have opposite truth values. So a proposition and its negation always have opposite truth values. And then what else did we cover? We covered the basic operations that you can apply on propositions. So just to remind everyone, I'm assuming that maybe half the class hasn't watched the previous lectures, so let's write it up again. We have P and Q, and those are propositions. You can have 4 possible combinations of true and false between them. You can have that's true and that's true. You can have true, false, false, true, and then finally false, false, for any 2 propositions that you have. Okay. Now, when considering propositions, you can look at operations between these propositions. So just like in arithmetic, you have numbers and you have operations like multiplication between them, addition between them, subtraction between 2 numbers. But we can do the same thing with propositions. We just have to come up with the definitions. So the first definition that I introduced was called the disjunction between P and Q. So this was a disjunction. You'll rarely hear me say that though, because this is read P or Q. So for all of you that have some programming knowledge, think about the OR operation for Boolean statements, right? And the disjunction is true when at least one of the 2 things is true. So we have true, 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 but it's false when they're both false. Okay. So P or Q is true when at least one of the 2 is true. Next operation was the conjunction. P and Q. And can you guess how I would read that? Just take a guess as a programmer.
P and Q.
Yeah, P and Q, right? So P and Q, that guy, is true only when they're both true. Or in other words, it's false when at least one is false. So true, false, false, false. And by the way, this is a truth table. It's just a way of illustrating the definition, right? It's also a way of verifying equivalencies, which I'll get to in a moment. So the next operation is called the conditional. Okay. This is the conditional. And this is read if P then Q. Or another way to say it is P implies Q. And there's some special terminology here. P is the hypothesis, Q is the conclusion. So if hypothesis, then conclusion. Okay. And the conditional, I'll just write out what it is. There are the associated truth values for the conditional. It's only false when you have a true hypothesis and a false conclusion. That's the only time that the conditional is false. That's how you should think about it. In particular, it's confusing for students sometimes that false hypothesis always has a true overall value, which these here are called compound propositions. When you have propositions strung together by some operator, there's compound propositions. Okay, so finally, I introduced what's called the biconditional. So, this is read P if and only if Q. Okay, and the biconditional is true whenever P and Q have the same truth values. Okay, so if the two propositions have the same truth values, then it's true. False other things. So, just as an example, like if P is the statement UHD is a public university, and Q is the statement 2 plus 1 is equal to 5. But then we look at these as like, do the definitions make sense more or less? So, all right, so let's look at like the or between two, right? So UHD is a public university, or 2 plus 1 is equal to 5. This is a true statement because at least one of them is true. Or if I look at the conjunction, that would be UHD is a public university and 2 plus 1 is equal to 5. That's false, right? The conditional, so this might be weird, but like, let's do if Q then P. So if 2 plus 1 is equal to 5, then UHD is a public university. That's true because the hypothesis never was satisfied. So for those of you that program, imagine you have a script, and then in that script, you have a conditional, and then underneath that conditional, there's code that doesn't run. Right? Like if you crash it, right? But if the conditional is never met, it's always false, nothing bad happens. Right? So this is what's called vacuously true. If the hypothesis is never true, then the whole statement is true. Right? It seems a little bit off, but if you think of it in terms of programming, hopefully that helps. Right? If the conditional is never met, you don't have to consider what comes after it. You only have to consider when the hypothesis is met. So for example, if UHD is a public university, then 2 plus 1 is equal to 5. That's false. Because the if statement, this is true. So then you have to check the conclusion, which is false. Okay. And for notation, I need to also remind everyone that the negation of a proposition is this. So if the original proposition is true, the negation is false. If the original is false, negation is true. Yeah. So again, I go into much more detail in the previous lecture. I'm just trying to get everyone caught up because not everyone saw the lecture. Okay, so we have propositions, declarative statements, either true or false. We denote them by lowercase letters. We have or, and, if, then, if and only if. And we're going to learn to derive more complicated compound propositions. So if any of you have ever taken your pre-cal class, maybe you looked at trig identities. We're going to look at propositional identities. That's what this lecture is going to be about. So, yes.
Any excuse version, please.
Yeah, always feel free to walk away, and I'm recording these, so you'll be able to get caught up when I post them, right? And some older professors don't like it when the doors shut and close, especially when they're recording it, but it's fine. Okay, so I need to remind everyone or introduce everyone to the notion of compound propositions being equivalent. So again, this is from last time, just remind me. So compound propositions P and Q are logically equivalent denoted by that. So by the way, I'm using P and Q, but P could be equal to like R or S, but your compound propositions, not necessarily just one of them. Okay. So logically equivalent, that's the notation. Whenever the biconditional is always true. Okay. So if something is always true, I go into detail in the previous lecture. This is called a tautology. It's always true. A compound proposition that is always false is a contradiction. And if it depends, it's called a contingency. It's just terminology. Okay? I don't think we need that terminology to understand what it means for things to be logically equivalent. And I'll give you an example. Okay, so let's look at a claim. By the way, whenever I write claim, like so, I claim that the negation of P or Q, I claim that's logically equivalent to not P and not Q. Whenever I write claim, do not assume that it's true. Okay, you need to verify that it's true on your own, or I'll verify it for you, but do not assume it's true, because sometimes I will give you claims that will be false, and it's up to you to check that. Right? Okay, so how could we argue this is true? Well, this symbol here means that these are logically equivalent, which means that if and only if that is always true. Okay, and the if and only if, the bicondition means they always have the same truth value for the future. So we can show this with a truth table. Again, we just have to basically enumerate all possibilities of true and false between P and Q. So true, 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 false, false, true, false, false. And then after we enumerate all possibilities for P and Q, then we just have to look at the truth values for that side and the truth values for that side. Okay. So first we should probably do short Q. So true, 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 false. And then now we're going to look at the negation of it. And as I mentioned, the negation always has the opposite truth value. So we just convert that to false, so false, 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 true. Okay, so we know all the possible values for that. So now let's look at the other side. Not P and not Q. So remember, and is only true when they're both true, right? So we basically look at not that and not that, not that and not that, and see what happens. Okay, so false and false is false. False and true is false. True and false is false. And finally, false and false. Oh no, true and true is true. Now, technically, we would maybe make sure it satisfies that definition. That's 4. Logically, please look at the biconditional between those. We want to show that the biconditional between those two sides is always true. So again, it might seem quick, but just to remind you, the biconditional is true whenever they have the same truth value. So false if and only if false, that's going to be true. False if and only if false, true again. They all match up. So we're going to have true all the way down. So yes, these satisfy the definition of being logically equivalent, and we've established an identity. Okay. So this is one of 2 very important logical equivalences that have a name, and these are called Demorgan's laws. Demorgan's laws for logic. There's a Demorgan's laws for sets, but we're in logic right now. So, okay, so and these just say this. So the negation of P and Q logically equivalent to not P or not Q. And then this one we just proved the negation of P or Q is logically equivalent to not P and not Q. So those are called Demorgan's laws. And we verified one of them, this one. We should probably verify the other one. Just make a truth table and verify it. Now, please, all you CS majors, know it doesn't seem very applicable, but do, don't forget these. Your CS professors would be bummed. Like I've had CS professors like talk to me about this problem. The students don't remember these laws. So why would they be useful to you? So for example, when we look at the final project and we're coding stuff up, there's a specific instance where we need to say that we don't want, we want, like, in order to enter into this one loop, we don't want this, the negation of one thing and another. So, but instead of programming, like using that in the if statement, you just do that, if that or that. And it makes it easier to program, right? Instead of trying if in parentheses, it's just easier to do this. Like if not P or not Q. When we enter into the loop, and then we do the thing, right? So these laws are especially applicable in those types of scenarios where you have a conditional that's a little bit more complicated than you want to actually type in, and you just switch it over to an or, you switch it over to an and. And they're actually pretty easy to remember. Just think of it like distributing the negation in. So change that, change that, change that. See what I mean? Same thing here. Change that, change that, change that. It's not, there is a distributive law we're about to look at, but just think of it like distributive, right? Like the negation is going into the parentheses. The and becomes an or, and the or becomes an and. Okay, so I hope that kind of illustrates what it means to be logically equivalent, right? And that's one set of laws. Okay. Okay. So in the Discrete Mathematics and Applications textbook, which all of you should be able to find a PDF book online, 7th or higher edition. In chapter 1.3, there's a big table of logical equivalences. So I think I wrote down enough to where you don't have to pull it up. So give me a second to write down this table. All right, so so maybe we can just reason why this is true real fast. So P and true is logically equivalent to P. P or false is logically equivalent to P. So why would this be the case? Well, you can just say, put in the two possible options and see that it's always that case. Okay? So in order for this to be true, P must be true, which means that that's going to be true. Okay? In order for this to be true, P must be true. Okay? If P is false, the whole thing is false. Okay, so then you see that they match up, and I think these are called the identity laws. The identity laws, so those two. So there's some other simple ones. So what is P or true logically equivalent to? P or true? What do you think that's always going to be? True, right? Because the true like makes it true, right? And then if you have P and false, what's that going to be? Always false. False, right? Because there's no way for it to be true. So it like forces it. I think that's why these are called the domination laws. Also, this is an example of a tautology. This statement's always true, no matter what the truth value P. This is an example of a contradiction. And no matter what P is, it's always false. Okay. And then also, these are kind of dumb or straightforward. Right? That would make sense, right? Whatever choice of P is going to make that vote, right? Those should make sense. So these are called the idempotent laws. Idempotent. I'll never use that word. This is obvious. These will have the same. What else as far as simple goes? There is this one. So if you negate the negation of P, what do you think you get back as a truth value? D, right? It just changes it back. So this is called the double negation law. That one's used quite a bit. Okay. What are the others? Distributive, commutative, associative laws, just like in arithmetic. So, commutative, so P or Q, logically equivalent to Q or P. And then P and Q, equivalent to P, Q and P. So these are commutative laws. And then we have associative laws. So P or Q or R is logically equivalent to P or Q or R. And the same thing for the AND operator. this is just associativity. Okay. And then there's two more. So the distributive laws, the P or Q and R. So you can think of it just like distributive. Take that with that, and then and that with that. So it will be P or Q and P or R. You see what I mean? And then if you have P and Q or R, that's logically equivalent to P and Q, and then or P and R. So these are called distributive. And technically speaking, we need to verify all of these with a truth table, but it's kind of tedious. And I think in the design book, you'll do this with truth tables. Now, there's one more law that I want to write down, and that is if P then Q is logically equivalent to not P and Q. Not P and Q. This one doesn't have a name, but I call it just star. So that's what I just call it, star. Okay, so with all of these here, we can derive pretty much any other logical equivalence that you'll see. So let's find an example of one. So what does this one say? This is negation. Oh, this is an important one. So claim that the negation of if P then Q is logically equivalent to P and not Q. Okay, so we could establish this with a truth table. We could, that's fine, but we can also use all of this information here. You're allowed to use these equivalencies to derive that statement. So how would that look? So suppose we want to prove it. So poof. Okay. So we can start on one side and then string together a bunch of these things to get to the other side. Now, as a general rule of thumb, you're probably going to want to get rid of conditionals first. They're the most annoying. Okay. So I'm going to start on the left-hand side. So we're going to get rid of that conditional. Oh yeah, Demorgan's laws are also in that list of things that you can use. So these guys here. Okay. So to get rid of that conditional, I'm going to use star. Right, so I'm going to say that this is logically equivalent to negation of not P and Q. And that's by star. So I state the rule that I used. And that way, if a reader is looking at this and they see, okay, they want to verify it, they can look up the rule and then say, okay, that line's at least good. Okay. So now we have the negation of an and, right? So we can use Demorgan's law, right? So this will be the negation of not P, the and becomes an or, and then not Q. And that's by this law, so by Demorgan. You know, I'm running out of room, but I'm trying to write it big so it picks it up on the camera. So from there to there, we can verify by just looking at that. So now what law am I going to use, you think?
double negation.
Right, double negation. Negation of P, the negation of not P is just P. That's by double negation. And did I do something wrong? It looks like something's up. Ooh, did I write down this symbol wrong? Let's see. Something's up. What is it? P or not? Ah, I don't know why I wrote it down wrong. So star is an or. Should have caught that. Okay, so it should have been an or. So going back over here to fix it, that should be an or. And then when we send in the negation, that or will become an and. Pop that earlier. But okay, so now look, we have that on the right hand side, the left hand side, we're good. We're done. We can just put our little QED box, and that's the end of the proof. We've shown that these are equivalent. Good. Okay, so let's maybe look at another one. Any questions though on that? It really is just like looking to what you can use and then just stringing it together. Or you could use a truth table. A truth table would also do that. How would you do that? With a truth table, you would fill in a column for that, fill in a column for that. If they have the same values all the way through, they're logically equivalent. Okay, so let's look at another one. So hopefully I wrote this down correctly. Negation P or not P Q. Logically equivalent to not P and not Q. Okay, so this one's a little bit longer, right? So the first thing I saw, you want to start with the more complicated side and then like simplify it down. It's a lot easier to simplify down than it is to expand out. So to the left hand side. So what rule do you think I'm going to use first? It's not on the board, I erased it, the Demorgan's law. You have the negation of the or. And so whenever you see a negation of an or, you can just always apply the Demorgan's law. So this will be not P and the negation of not P and Q. You have to be very careful when you have a lot of these symbols to take your time on it. All right, so what do you think I would do next?
Distribute the negation.
Yeah, so apply Demorgan's law again. And technically, it follows like you should write by whatever law you're using. Okay, so, all right, so let's do that again. Let's use the Demorgan again, not P, and negation of P, the and becomes an or, and the negation is Q. And that was by Demorgan. So what law do you think I'm going to use next? Double negation. Okay. So now, let's see, so not P and P or not Q. And that was by double negation. So now what do you think I'm going to use? You have something and then inside parentheses or. Distributive law, right? It's the only thing you can really use. So this would be not P and P, or not P and not Q. Like that. So by distributive. Sure, did that right? Not P and that, or not P and not Q. Okay, so now what?
Not P and P is false.
Right. Not P and P. So the conjunction of two propositions has to be true whenever they're both true, right? And since propositions are either true or false, there's no way that this could be true. This has to be false. This is a contradiction right there in that proposition. And then what's the next law to use? It looks like to me that it's going to be the identity. Right? Proposition or false is just the proposition. And what's the goal? We're trying to get to that, and I see it right there as well. So this will be not P and not Q. And that's by the identity. And then we're done. All right, we've established that these are logically equivalent. So I'll give you a moment to write that. I'll write down another one for the footnote. Okay. All right, so following claim. P and Q implies P or Q is a tautology. In other words, it is always true. So if we can string together a bunch of logical equivalencies to show that we end up with a capital T at the end, then we verified that, right? So we want to show it's always true. But it's a conditional. Is there another way to show that it's always true. So the conditional, if you look at your notes, when is the conditional false? Only when one thing happens. The conditional is false. Remember, the if part is the hypothesis, the then part is the conclusion. So when the hypothesis is true and the conclusion is false, right? The conditional is only false. The only possible time it could be false is when the hypothesis is true and then the conclusion is false. That's the only time, right? So, like, if this part is false, the whole thing is true. We don't have to worry about anything because if you have a false hypothesis, the whole thing's true. We only have to worry about when that's true, right? That's the only time we have to check, since otherwise it's going to be true, and we're trying to show that it's always true, right? So we can prove this with a truth table, we can prove this with logical equivalencies, or we can do something like I'm about to do, and just use reasoning and definitions to argue why this is true. Okay. So we can say if P and Q is true, wait, so if P and Q is false, then P and Q implies P or Q is true by definition. Right? Like if the hypothesis is false, then it's true. This is by definition. Okay, so that checks off one of the ticks. We just have to now consider when the hypothesis is true now and see what happens. Let's just go down the rabbit hole. If P and Q is true, do we get any information if we assume that? If we assume P and Q is true, do we get any information to work with? Do we get any information? If that's true, do we know anything new? What must be the truth value of P? It has to be, right? Because the conjunction is only true when they're both true. So what must be the truth value of Q? True. So here's the thing. We made an assumption, and then we got new information out. So if that's the case, then P is true. And Q is true. Right? It must be the case that that happens. Okay. Then P or Q is true. Right? And the full statement must be true. In both cases, if the hypothesis is false, then the whole thing is true. That's like the simple case. That's called the vacuous case. If the hypothesis is true, then it implies that the whole thing must be true. And then we're done. So we learned 3 levels of verifying identities. 3 levels of proof techniques, basically, for these things. We can prove logical equivalencies with a truth table. That gives us the least amount of information. Right? If our goal is to understand things, the truth table gives us the least amount. If we string together logical equivalencies, we gain a little bit of information about how this thing gets transformed to this other thing, right? We gain a little bit of information about that, right? But still, when we string together the logical equivalencies, we didn't understand. So what do I mean by understand? Why is that always true? I can just tell you. If the hypothesis is true, both of those are true, and then those have to be true. Done. That's why it's true. Why that thing is always a tautology. See how there's a difference? Like, we can talk it out now. We can describe it in like language, which is how we communicate. We don't communicate in symbols, we communicate in language. So this is like the highest level of argumentation, because now we get it. And now we can discover new things just by thinking about it. In particular, like, if we have like, if we can just, if anything here means that these things have to be true, we can probably come up with new ones, right? Like, I could stick like an and there, and I know it's going to be true, right? Because we knew that both of these things must be true. Okay. So this is what a mathematician would do. So most of you have like literally no idea what mathematicians do. The math that you've taken up to now, and even by the time you finish your degrees, none of you are math majors, like, you won't have seen what real, like, actual mathematics is. Real mathematics is not about symbols and messy, like, stuff like that. It's really about explaining. It's about assuming something, and under those assumptions, what happens? And then explaining why those things must happen the way they do. It's like telling a story. Right? Mathematicians philosophize about ideas. Mathematics is all about ideas. And that's like what led me to become a mathematician, is that it's about storytelling in a sense. And a lot of mathematicians are writers. They're very creative people. Lewis Carroll, the author of Alice in Wonderland, Looking Through the Looking Glass, right? Lewis Carroll was a mathematician. There's other examples of this happening in the history where the idea of telling a story is important because we're communicating with each other. I hate it when I see like nasty math, like equations all over the place, and it hides everything. It hides the ideas. Right? Like when you look at like the prime on an F symbol to denote the derivative, what's going on there? That prime is like hiding like the actual ideas. And the idea is that something is changing over time. That's it. Right? So in your other, like when you take other math classes, please try to remember that. Like when you come across an idea and you're doing these like equations and you're calculating things, because that's what you have to do in your classes, remember that there's an idea that makes it a lot easier if you try to like really get the idea. Okay. And then you don't have to remember as much. Like I have a terrible memory. I forget everything, but I'm able to put it together into like a concept and then slowly figure it out from there. Okay. And this will help with a lot of things like programming. Like I forget syntax all the time, but the general idea, I know that there's a story to be told. How do I get there? And okay, so I think that I should probably stop here because I would like for all of you to go and watch lecture 1 so that all of this makes more sense. And then you can watch this one again. I'll post it after class. Be sure to look at the homework. And then also from the Rosen book, I would definitely read section 1.3. So Rosen 1.3, read it, look at the exercises, try to do the exercises. The solutions are in the back. And then also definitely start homework 1. It's in the side book. Okay. I'll see y'all next time.